Welcome back to part two of week two of meteorology and climate change. How are you guys doing? Let's get started. All right, so this video is going to be about absorption, emission, and the equilibrium of our incoming solar radiation. So we're going to go over things like the enhancement of the greenhouse effect, warming the air from below, Earth's energy balance, and then also our seasons. So first, we do have a natural greenhouse effect. The greenhouse effect isn't just from what we're doing and we're putting into the environment. There actually is a natural greenhouse effect. Um, so this is going to be the resulting 33 degrees Kelvin increase in temperature from the equilibrium temperature of the Earth, which is 255 degrees Kelvin. That's what it would be with no atmosphere. So the natural greenhouse effect is basically going to be, how much is our atmosphere causing us to warm? Now, that's just naturally without, what we're putting into the atmosphere. There are ways that we naturally warm and, keeps us warm, which is good. Otherwise, our planet would be freezing and we wouldn't want to live here. So the natural greenhouse effect, exists because of a naturally occurring greenhouse gases. So we do have natural greenhouse gases, which is also good, particularly water vapor and carbon dioxide. So carbon dioxide isn't just bad. What's bad is what we're putting into our atmosphere over and above what's already there. So all planets in our solar system have a natural greenhouse effect, and the strength of the greenhouse effect depends on how much atmosphere it actually has and what the atmosphere is actually made of. So the natural greenhouse effect, we just went over, is the greenhouse gas. A greenhouse gas is a gas that is largely transparent to the sun's UV and visible radiation, but selectively absorbs and re-emits long-wave thermal IR radiation that is emitted from the Earth. Because remember, we basically have incoming visible radiation, and then we're going to warm, the ground, and then the ground is going to have that IR radiation that's going to be emitted from that. So a greenhouse gas is basically going to be something that's going to let the visible through, let the UV through, but it's going to absorb this IR radiation. Well, what is IR radiation but, heat? So it's basically going to warm the atmosphere. So, that in itself is good. Like, if we want a certain amount of that going on, otherwise we'd be freezing, really, really cold here. We wouldn't want to live here. So the natural greenhouse gas is fine. But it's once we get into the anthropogenic realm, which means originating in human activity, or what we're actually putting there, which is kind of throwing it, well, it's not kind of, it is throwing things off of balance. So, we have over here natural greenhouse gases with 60% water vapor, 26% carbon dioxide, and then 14% others, things like nitrous oxide and methane. These are all naturally occurring within our environment, good to go. Then we also have anthropogenic greenhouse gases. These are going to be the ones that are not naturally there, that are originating in human activity. So this is going to be things like the additional unnatural CO2 emissions, the additional unnatural CH4 emissions, the CFCs, other synthetic fluorobromocarbons, tropospheric ozone. Remember, it's okay and normal in the stratosphere, but in the troposphere is where it's bad. And then also nitrous oxide. So the greenhouse enhancement is going to be the increase above the natural greenhouse effect. Okay, like above what naturally would have been there, what is caused by anthropogenic means or human-induced means, what we're actually putting, the increase that we're putting on the planet. So these are going to be two depictions, basically. One is without the greenhouse effect. So this is going to be our incoming shortwave solar energy, and then our outgoing infrared energy, from our planet. And then over here, when we look at it with the greenhouse effect, we have our incoming shortwave energy, and then a portion of this outgoing long-wave IR energy is actually going to be absorbed by the atmosphere. Now that's going to be the thing that's going to cause that additional warming. This is going to be with the greenhouse effect, the natural greenhouse effect. I know this because, it says 59 degrees Fahrenheit, which is pretty much the global average. Okay, so this is what we have going on, since we have an atmosphere. This is what's going to happen, without an atmosphere. And then the anthropogenic or the greenhouse enhancement is going to be what happens over and above this. So more gases in our atmosphere, which is going to cause more of this infrared absorption going from that long wave radiation. Okay, so this actually is showing you exactly how efficient, there's a couple of these graphs I have put in here, how efficient different greenhouse gases are at absorbing, and in which spectrum that they actually are going to absorb in. So you can see that this right here, from like about here to here, this would be like the UV spectrum. Right here to here, this would be in the visible spectrum. And then from here to here, this will be in the infrared spectrum. So this is carbon dioxide, water, ozone, this is everything, the total atmospheric absorption. And this is the percentage over here on the y-axis. So you can see that if you look at like everything combined, that our atmosphere is perfect at letting in the visible light, but absorbing almost everything else. Okay. Also in this in the IR window, it lets out the infrared. It keeps a certain amount of it. We want to keep warm, but it really is a perfect filter, and only lets in the things that we want to let in and lets out the things that we want to let out. So here's the absorption spectra for our CO2. You can see that it doesn't absorb at all in the visible range. It doesn't absorb at all, in this range right here, but it definitely is a very good absorber of this, like the heat. This is why carbon dioxide is a greenhouse gas, because it is selectively absorbed within this window right here between here and here. And this is heat. So it basically is going to absorb all the IR, outgoing IR, okay, the infrared, and it's going to let through all the light as well. So that's why we call them greenhouse gases, because it's like a greenhouse. It lets that light in, but then once it turns into heat, it doesn't let the heat out. The same as a greenhouse does, for plants. Also, if we're in our car, it does the same thing. The windows do that, if you're sitting in your car, it gets really hot as you're sitting there. You can see that there's also absorption spectra for water. It lets in all the visible, and it selectively absorbs here, some in the heat, in that IR, some over here. But generally speaking, it lets through what we want it to let through, and it lets out what we want it to let out. And you can see right here, this is the ozone right here, that O3. O3 right here, it absorbs all of this in this, UV range. Again, that's good. That's what we want it to do. Okay, because that's what it's doing, is not letting it through to us so that we don't get harmed by it. Here's some of those group questions. I do encourage you to, pause this and see if you can answer these on your own. All right, so, I think I put in at the beginning that we're going to go into air is warm from below. I don't know if you were aware of this or not, but I think a lot of people think that we're actually warm from the sun and we're warm from above, but that's not actually what's happening. The sun, you can see here, has the shortwave solar radiation, which is coming down and hits the ground, and through conduction and convection, okay, and also latent heat release, is actually going to cause this to circulate and mix throughout our atmosphere, and it's going to warm us. So really what's happening is the ground is getting warmed, and then through conduction, the air right above the ground is actually getting warmed, and that's how our planet is actually warmed. Okay, and you can also see the absorption and emission of infrared radiation by water and carbon dioxide does actually happen here. So, we have the solar radiation coming down, we have the conduction going on, it'll warm up things, we'll have some of it leave, but some of it actually be absorbed in the atmosphere here, and you can see that it's actually going to come back down to the ground, some of it's going to be radiated back up to the sky, and this is where it's been warming here. So a certain portion of this we want, it's the amount over and above what's supposed to be there, because then it throws the balance off. Speaking of the balance, we do actually have an energy balance. So if you look at each, piece of solar radiation as a unit, and that each, like 100 units are incoming, we have 51 absorbed at the surface, We have about 19 absorbed by the atmosphere and clouds. We have some of them reflecting off the Earth's surface. We have some reflecting off of clouds, some reflecting off the atmosphere, where about 30% is reflected and scattered, off of these three things. So about 30% goes back out into but 51 is going to be what's absorbed, and, 19 over here. So the thing that's not good about, you know, greenhouse enhancement or climate change that we're speaking about is how we have that carbon dioxide and we're putting more of it into our atmosphere than should normally be there. And because there's an increase of CO2, now all of a sudden it's not going to be 19 absorbed by the atmosphere, it's going to be a higher number, which then is actually going to cause the atmosphere right here to warm up. Some of it will come down to us, some of it will come up here, but either way it's going to warm up this atmosphere, and it just kind of throws this balance off. We need everything to be in balance in order to stay at that steady temperature that our global temperature, if you average it all out, that we should be at to live here comfortably. Okay, and like I said, each beam of incoming solar sunlight can either be reflected back out into space. I went over this in the other set of slides, but which the amount that's reflected back into space is going to be the albedo. Clouds and atmosphere surface, these can be reflected or absorbed. But what influences incoming solar energy per area each day? Like what, when we're looking at the balance and we're looking at how much solar energy is coming in, what determines that? So, there's two main things: the angle that the incoming solar ray actually hits, which is the angle of incidence that hits our planet, okay, and also the length of time that the sun is actually in the sky. So the lower the sun angle, the angle of incidence, that means the less incoming solar energy per area. And the higher means the more. And obviously the summer, we're going to have more sun hours, and during the winter, less, because this right now is the winter session. Well, we're in the winter right now, so we all know it gets like dark really fast outside. Gosh, it's like barely get off of, work and we go home, and at least for me, it's like, it's already nighttime. So, those two things are going to be the things that factor how much solar energy that we receive. Now, these things are caused by the tilt of the Earth's axis. The axis does point to the same direction in space all year round. So it's going to kind of go like this. Here, I have a picture of it. So you can see how that tilt is going to just be the same direction. It doesn't go like from facing that way to facing this way. It's always going to be facing in the same direction, and it's at 23.5 degrees. So another little fun fact for you, it's not as apparent in this diagram, but I have other ones that it is. Actually, see, this is December 21st. Can you see how it's actually like closer to the sun right here than it is right here? That's because we're actually closest to the sun in our orbit during the northern hemisphere winter than we are during the northern hemisphere summer. Now, you can see that they receive the same because it's hitting. Right now, it's hitting actually right down there in the southern hemisphere. And right here, it's actually hitting more in the northern hemisphere. And right here, it'd be the same because it's just parallel. So this is actually where we get our seasons from. This is going to be winter for us in the northern hemisphere because it's tilted away, and summer in the southern hemisphere. And right up here, it's actually going to be hitting, right here at the Tropic of Cancer more. So this is going to be our summer, but the southern hemisphere is winter. And then this is going to be, fall and spring respectively. But why in the world would that tilt matter? Why does this tilt make such a difference with our seasons? This is actually where this whole, business of the angle of incidence comes in. Because if we're like right here and it's getting direct beams from the sun, that would be like right here. See, from that edge to that edge, how there's not that much space. These people are receiving in the equator, just a ton of solar energy per area because it's not spread out very far. But right here, it's spread, that yellow is spread really far, and right here is spread really far. So the same amount of energy is going to be spread out over a larger area. So that means that they're not actually going to get heated as much. So, when the sun hits up here, then it's going to be summer and it's going to be winter down here. And when the sun is hitting down here, then it'd be summer down here and winter up there. Although the equator receives the same amount the year round. So here's another idea of it. The sun being lower in the sky, like during winter, right, is spread out versus higher in the sky. This is not spread out very much at all. These guys receive just a ton of that solar energy. There's another way of looking at it. Here's our December sun. You can see, it's lower in the sky. We don't, the daytime is not as long, 7:30 to 4:30, where this is going to be like, 4:30 to 7:30. So you can see right here, these guys are going to receive a lot more sun. And then as you saw before, it's going to be higher in the sky. So they're going to receive all these direct rays. And here's some more group questions. So this is the end of the second part of week 2. I hope you guys have a good week. If you have any questions, please email me. And thank you.